In the last few classes we concentrated on the T naught concept and then its utility for us, and in that connection we spent sufficient time, quite a significant amount of time, on glass formation. And all of you know glass formation you have seen with respect to a eutectic phase diagram. Usually you see glass formation only when there are eutectics, because why? Because eutectic is where the liquid is stable. The meaning of eutectic is the liquid, the melting point depression, isn't it? Many of you know eutectic means low melting. So with respect to the two pure metal melting points, the eutectic always has a lower melting point. Lower melting point basically means liquid is stable, isn't it? So if the liquid is stable, then only you would get a glass. If the solid is stable, you won't get a glass. So in that connection we talked about glass. Today let us go a little more detail into the eutectic, not talk about glass formation but about eutectic itself. So see how the eutectic solidification occurs. For example, if you take a phase diagram like this, something like this, you take a eutectic composition, and the moment you come below the melting point, below the eutectic temperature, bring this liquid, hold it at this temperature, what should happen? Liquid should give you alpha plus beta, and this should happen by a nucleation and growth, isn't it? Because the liquid composition is different from the two solid compositions, whatever the two solid compositions are. So this is liquid, this is alpha, this is beta, this is liquid plus beta, this is liquid plus alpha, all this you people know. So now if I take the liquid and bring it to a temperature T below the TE, this liquid should give you alpha plus beta, and this alpha plus beta microstructures, there are variety of these microstructures. The most common microstructure is what is called a lamellar microstructure. You also might have heard about what is called divorce eutectics. If possible, today's class itself we will talk about why various types of eutectics come. That is again related to what is called surface energies, which is a part of the thermodynamics. We will look at it. But if you simply look at this alpha plus beta, which is nucleated inside a reservoir of liquid, so you have a liquid here, and this nucleus, a couple which has nucleated, alpha and beta always nucleate together if it is a lamellar eutectic. If it is not lamellar eutectic, they will not nucleate together, that also we will see it later. But assuming that they nucleate together, how do they grow? If they want to grow, what you see is that alpha is a A rich phase, beta is a B rich phase. So A rich phase and a B rich phase, both of them are growing together into the liquid. How do these two grow? They can grow only when the liquid supplies atoms to alpha and beta, isn't it? Atoms are actually coming from the liquid to alpha and beta, they are joining alpha and beta, and as a result the alpha and beta are growing together at the expense of the liquid. So that at the end of the reaction, if I do what is called the cooling curve, temperature versus time, at this particular time this has nucleated, and as I grow by this time all the liquid should vanish and everything should become alpha plus beta. Of course there are a number of such couples nucleate at various positions, a number of nuclei, and all of them grow together, such that they form what are called certain boundaries. What do we call those boundaries as? They are not grain boundaries. In a eutectic you do not call them as grain boundaries, because there is, it is not a grain boundary is related to one single phase, there is no one single phase here. So what do you call when the eutectics, this nucleates here and somewhere else you have something else nucleating here, alpha plus beta, both of them come together and meet each other, what do you call that boundary? Of course, it is an interface. Even this is also an interface, isn't it? So, there is a name, because this is called a eutectic colony, and what you get them are called colony boundaries, eutectic colony boundaries. So, you have a number of such eutectic colonies grow, and you will have eutectic colony boundaries coming in like grain boundaries. They are analogous to grain boundaries, and you would see in most of such eutectic microstructures boundaries of different alpha beta growing in different orientations. Between each colony, the difference is the orientation of alpha beta couple. So, the alpha beta couple orientation in this and this orientation is going to be different. So, it is similar to grain boundary where you have grain orientations are different at the boundary. So, now forgetting about that. So, basically this alpha beta grow at the expense of the liquid. That means what? For alpha beta to grow together, you need liquid to supply more A atoms to alpha and more B atoms to beta. This is a very tricky problem. How is that? The liquid which is there in front of it is selectively able to supply more A atoms to alpha and more B atoms to beta, such that they grow together. It is one single liquid. One single liquid is able to supply more A atoms to alpha and more B atoms to beta. Unless you do that, if only certain atoms, let us say A atoms are coming uniformly to both the things, only alpha will grow, beta will not grow, then it will not be a coupled growth. So, if you want a coupled growth to happen, this has to, so that means selective supply of atoms to alpha and beta should take place. And how does this happen? It happens if you understand the thermodynamics a little bit. So, let us try to see what happens when we draw a free energy composition diagram at a temperature like this. I have taken a liquid of eutectic composition, brought it to this particular temperature. At that temperature, this whole thing is happening, and I am trying to look at what is happening. So, if I draw the free energy composition diagram at that temperature, how will it look like? What is stable at that temperature? Can you tell me? Alpha plus beta. So, that means alpha and beta curves, free energy curve should be below that of the liquid. By now all this should be clear to you. So, if that is the case, I can easily draw. So, I can draw a liquid and I can draw an alpha and a beta and draw a common tangent between them. So, this is the alpha curve, this is the beta curve, this is the liquid curve, clear. And these two compositions where you have the common tangent of alpha and beta should correspond to these two compositions in our phase diagram, am I right? So, because there has to be a 1:1 correspondence between the free energy composition diagram and the phase diagram, and this is the GX diagram, free energy composition diagram. Now, if I look at again our couple, once again alpha and beta, you have a liquid here. So, this alpha is in equilibrium with liquid, this beta is also in equilibrium with liquid. Now, let us look at in this free energy composition diagram what represents the equilibrium between alpha and liquid and beta and liquid. Whenever I say equilibrium, it is represented by what? In a, it's a common tangent. So, when I say an equilibrium between alpha and liquid, I should draw a common tangent between alpha and liquid. So, how do I draw a common tangent between alpha and liquid? See, something like this. So, you have this composition and this composition, and let us first give certain notation for the first two compositions that we have already drawn. What is this? This is the composition of alpha in equilibrium with beta. This is the composition of beta in equilibrium with alpha, am I right? And what is this composition now? C alpha liquid, and this is C liquid this is C liquid alpha, am I right? Now, similarly let us do the same thing for the beta. So, if I do this, some 2 compositions again you get, we are getting totally some 6 compositions now, and this composition is, if I put it, this is C liquid beta, and if I identify this composition, this is C beta liquid. What am I getting out of all this? Just simply certain 6 compositions we have got, but if I carefully observe these 6 compositions, forgetting about the first 2 compositions which are between the alpha and beta, look at these 4 compositions. If I compare the composition of liquid in equilibrium with alpha and the composition of liquid in equilibrium with beta, I get some information. What is the composition of liquid in equilibrium with alpha? It is this. This is the composition of liquid in equilibrium with alpha. This is the composition of liquid in equilibrium with beta. What does that tell you? That tells you that the liquid which is in equilibrium with alpha has a higher B content when compared to the liquid which is in equilibrium with beta. This is the liquid which is in equilibrium with alpha. That means the liquid which is just in front of the alpha and the liquid which is just in front of the beta, if I look at the compositions of those 2 liquids, they are not the same. And not only that they are not the same, that the common tangent generation itself makes it such a way that the composition of liquid in equilibrium with alpha has more B content, the composition of liquid in equilibrium with beta, that is this quantity and this quantity, these are the 2 we are looking at, this quantity is higher than this quantity in terms of percentage B. That means what? Just in front of alpha you have more B atoms and in front of beta you have more A atoms, okay. And this means that liquid is not having the same composition everywhere. If I go far away from this alpha plus beta interface, what is the composition of the liquid? It is same as that of the eutectic composition. It is only because of the local equilibrium that has to be maintained for this alpha, and if this composition is not maintained, then alpha and beta cannot exist in equilibrium with liquid. They will not lie, they will possibly dissolve back into the liquid. If alpha and beta have to exist with the liquid, the only way that is possible at this temperature we are talking about. Remember, if I am talking of at this temperature, situation would be different. At this temperature it is the same because it is a common tangent between all the 3, but we are talking of a temperature below the eutectic. I have brought the liquid below the eutectic and now looking at what would happen. If I am looking at that, you would see because of this, here at this position you have more B atoms than this. Then what you see is that B atoms will start travelling in this direction and A atoms will start travelling in this direction, and the gradient is decided by what is called this. What do we call it as? Interlamellar distance. Actually this distance, can you tell me what is this distance between the half of the alpha and half of the beta? Between the center of the alpha lamellae and the center of the beta lamellae, what would be the will it be the interlamellar distance, or what do you mean by interlamellar distance in a eutectic? You must have heard of this word interlamellar distance, okay. When I say interlamellar distance, what distance I am talking about? From what, where to where? Between 2 lamellae of what? Of the, correct. So when I say if I have an alpha here, beta here, another alpha here, okay, so this to this is the interlamellar distance, lambda. So basically this is lambda by 2 we are talking about, and this movement of atoms, B atoms going towards the beta and the A atoms going towards the alpha, will make sure that the alpha will get more A atoms and the beta will get more B atoms, so that both of them grow together. And this is driven by what? It is driven by the difference between the composition of this and this, which is what we call it as delta C, which is nothing but C liquid alpha minus C liquid beta. This and the gradient, concentration gradient, can be written as this by 2, this by lambda by 2. This is the actual concentration gradient, and if you say diffusion J is minus d dC by dx, the dC by dx for the flow of atoms comes from here. Once the nucleation has taken place, the growth is decided only by diffusion, isn't it? And the diffusion, you need a gradient. If there is no gradient, if the gradient is 0, there is no diffusion. So this gradient is provided by this. And how do I see this in the phase diagram? Can I see these 2 points in the phase diagram? Now C liquid alpha and C liquid beta, where are they in the phase diagram? Extrapolate what? Yes. So you have 2 liquidus here, one is called the alpha liquidus, another is called the beta liquidus. And what does alpha liquidus tell you? Alpha liquidus tells you at all temperatures what is the composition of liquid in equilibrium with alpha, and the beta liquidus tells you the composition of liquid in equilibrium with beta at various temperatures. So I want to know at this temperature T, what is that? So if I want to know what is the composition of liquid in equilibrium with alpha and liquid in equilibrium beta at that temperature, the only way I can find out is by extrapolating the 2 liquidus. So if I extrapolate the 2 liquidus, I get this, and this composition is nothing but Cl what? Alpha. This is nothing but Cl beta. And the difference between these 2 is actually the driving force for the growth of eutectic. If you want the eutectic to grow, and that is the reason why, if you carefully observe, at the eutectic temperature this difference is 0. Cl alpha is equal to Cl beta, because if I draw at the eutectic, it is actually a common tangent, isn't it? If you remember, I can draw it for you once again if you want. So this is alpha, this is liquid, this is alpha, and this is beta, let us say liquid alpha beta. So if I am trying to look at what is the composition of liquid in equilibrium with alpha, what is the composition of liquid in equilibrium with beta, they are the same at the eutectic. Once they are the same, this delta C is 0, and if delta C is 0, the gradient is 0. If the gradient is 0, the flux is 0. So in principle at the eutectic you cannot have a growth, you need a small undercooling, at least a small undercooling. It can be very small if there is a heterogeneous nucleation available, otherwise it can be slightly large, but you need a small undercooling so that you have a driving force. And that is why you can again see that if I extrapolate this to lower temperatures, the lower the temperature, the larger the delta C, am I right? And that means the larger the gradient, and as a result in principle you can see the growth rate has to be higher, but there is a catch here. What is the catch? The catch is the D there, the catch is the D. Okay. So we are forgetting that there is a D there also, and this D incidentally, see if you carefully look at these 2 curves, if I assume that these are linear, then I can assume that the delta C is linearly dependent on the temperature, isn't it? Because this difference can linearly increase with temperature if these 2 are linear. If these 2 are straight lines, not curved lines, if I assume them to be straight lines, then you will see if I plot delta C versus delta T, delta T is undercooling, I will see that this will be linear, and at delta T being 0, delta T has C has to be 0. Now, if I find out the D as a function of undercooling, if I look at the D, how does it change? How does the diffusivity change with temperature? It decreases, of course. In what fashion? Exponential. You be confident whatever you want to say. You are an IITian. Tell me, how does diffusivity change with temperature? That is what we are questioning. All of you have read from your BTech level at various stages, how does diffusivity change with temperature. There is a particular expression which we always what is that expression called? Correct. What is that expression called? It is an Arrhenius equation. Okay, fine. So, this tells you that the D is exponentially related to the T. You can see that D is D naught exponential minus Q by RT. Okay. So, you will see that the actual, if I plot D on the same plot, if I plot D, you would see D would decrease. I mean, I have actually drawn parabolic, okay. It is not actually parabolic, it is exponential. So, it decreases very rapidly as you increase the delta T or decrease the temperature. Increase the delta T basically means decreasing the temperature. So, our delta T is increasing in this direction. So, that means there is a particular temperature, critical temperature, beyond which you will see the diffusivity plays a major role. So, that is where you will see, in fact, we are not really talking about kinetics here, otherwise I can even talk about the whole growth rate, how does it change. In fact, lambda itself changes as a function of temperature. You cannot have the same lambda as a function of temperature. All these things, when you study any kinetics course, you will know more about it. So, you can see until certain temperature, we can always say growth rate is proportional to this undercooling, because the undercooling is what decides the delta C, and the delta C decides the dC by dx, and as a result I can say at temperatures closer to the eutectic temperature, the growth rate is always decided by the delta T undercooling. So, the higher the undercooling, the better. That is the reason why any eutectic mixture, if I pour the liquid metal into a metallic mode or to a sand mode, you would see the growth rates are different. In fact, you will also see not only growth rates, the lambda is also different. You will see get a finer lambda, again basically because the nucleation rate is higher, the R star is smaller. So, all those things become important, and you will see this. So, you can see that this problem of how liquid is able to supply atoms to alpha and beta, we are able to simply understand it just if we understand this diagram. So, you can see from thermodynamics very easily we can explain how does this come. Now, let us go to the second concept of what should be the nature of the eutectic. It does not always give you a lamellar eutectic. Can you tell me what is the type of eutectic in a steel, in a cast irons? Sorry, I should not say steels. You do not have eutectic in steels. In fact, that is what differentiates steels and cast irons. Have you ever known what is the difference between a steel and a cast iron? When do you call an iron carbon alloy as steel? When do you call it as a cast iron? Less than 2. Why? What is so sacrosanct about this 2%?
Because I am not entering into the eutectic region.
Yes. Yeah. The cast irons, that name suggests they are easily castable. Okay. and easy castability basically related to eutectic. So, cast irons are all those where you have a eutectic reaction, and in the phase diagram if you look at it, below 2% there is no eutectic reaction, is not it. So, remember the iron carbon diagram, iron cementite diagram, you would see that it is only beyond 2% you start seeing the eutectic reaction, and that is the reason why we call beyond 2%. It is not just it is a magic number, it is basically the phase diagram, the eutectic reaction wherever it starts we call them as the cast irons, below that we actually call them as steels anyway. So, coming back to that, and that also reminds me that we should also try to understand why an iron carbon diagram and an iron cementite diagram are different. Today we will try to understand that also. Before that we will try to see there are different types of eutectics we said. For example, we are coming back to our first question, the iron carbon cast irons, what is the type of eutectic you have? Lamellar. You people have not seen microstructures, you have what is called a second year physical metallurgy lab, many of you BTechs should have. What is the eutectic? If I take a white cast iron, white cast iron is a typical cast iron, the other cast irons where you get graphite is not actually decided by the iron carbon, it is a graphite which comes from the iron carbon, whereas the iron cementite diagram which we look at it, the actual eutectic reaction is liquid giving the gamma plus Fe3C, that is the eutectic. And where do you see that eutectic? You see that eutectic only in the white cast iron, you do not see that eutectic in any other cast iron, whether you take a grey cast iron or nodular cast iron, you see the graphite there, which is not a gamma plus cementite eutectic. Gamma plus cementite eutectic, which is called the ledeburite, is seen only in the white cast iron. So, what is the morphology of this gamma plus ledeburite? What is the morphology of the ledeburite? Is it lamellar? It is not lamellar. It is, you have cementite networks, you see, you are all microstructures, you are ledeburite. I am not asking you what is the cementite network you will actually see when you come to the cementite being precipitated from austenite. Hypereutectoid steels is what you are talking about. We are talking about cast iron and the eutectic mixture in the cast iron, not what is the microstructure at room temperature. I am not asking you what is the microstructure at the room temperature. After the eutectic reaction is over, if you see the microstructure, how should the microstructure be? You have basically cementite particles in an austenite matrix. That is why you, if you see white cast iron, you see chunks of cementite particles. Go back and look at Atlas of Microstructures ASM handbook, you will get all this. So, similarly, if you look at aluminum silicon eutectic, aluminum silicon again a very popular eutectic. Why is it popular, aluminum silicon? Where do you use aluminum silicon? Automotive, pistons particularly. So, there again you would see aluminum silicon eutectic, you have silicon needles in a alpha matrix, alpha aluminum matrix. So, you do not see it as a alternate lamellae of alpha and silicon. Can you tell me which eutectic has actually a lamellar eutectic? Now, I have given two examples of non-lamellar eutectics. Give me any one example of a lamellar eutectic that you know. It is not eutectic, madam, you are talking of eutectoid, I am asking eutectic. Which eutectic is lamellar? Yeah, no, you have never come across? All of you are metallurgists, at least many of you, majority of you. Aluminum copper is one, lead tin is another, these are all lamellar eutectics. Okay. If you take aluminum silicon and if you take iron carbon, these eutectics are non-lamellar and people call them as divorced eutectics. divorce, in the sense they are not together, the alpha and beta are not together, they are kind of separate. Why does that happen? To understand this, we need to understand the interfacial energies. Whenever I talk about alpha, beta and liquid, I have 3 interfaces. Am I right? What are the 3 interfaces?
Liquid to alpha, liquid to beta, alpha.
Correct. Liquid to alpha, alpha to liquid to beta, and alpha beta. So, if you look at these 3 interfaces, alpha beta interface, liquid alpha interface, liquid beta interface, all of them are associated with certain interfacial energies, is not it? There is a alpha beta interfacial energy, there is a liquid alpha interfacial energy, there is a liquid beta interfacial energy. And we have already seen that whenever you talk about a liquid to solid transformation, the barrier for the transformation is always the interfacial energy. Whenever I bring a liquid below the melting point, it wants to become a solid, because there is a driving force in terms of the volume free energy. The liquid has a higher free energy than the solid below the melting point, as a result solid wants to form, but why solid does not form is because of the interfacial energy. So, as a result, whenever you have this kind of 3 interfaces, the system would choose the one which has the lowest interfacial energy. If a particular system has alpha beta interfacial energy as the lowest, the system would like to have that particular interfaces maximized, so that the overall interfacial energy is what? A into gamma. This is what is actually preventing the, that is why if you remember delta G, we always write this 4/3 pi r cube delta GV plus 4 pi r square gamma, you remember this. Of course, there we have assumed a spherical nucleus, we are not talking about eutectics there, but if you talk about eutectics, the same thing holds good, excepting that these geometric factors will change. Basically it is, I can write delta G as V into delta GV plus A into gamma, am I right? So, it is this A into gamma to be minimized, so that even at a smaller undercooling the liquid can become a solid. The liquid wants to become a solid at as small undercooling as possible. So, it will choose whenever it has, for example, if it is having let us say pure metal solidifying, it has no choices of interfacial energies, there is one single solid nucleating out of that. There also it will search for if there are any heterogeneous nucleating sites. The moment there are heterogeneous nucleating sites, the liquid is very happy, because this gamma is very small there, because that is what is the meaning of an interfacial of a heterogeneous nucleation site. A heterogeneous nucleation site is that site where the interfacial energy between the solid that is nucleating and the particle that is available is very small, and that is the reason why you see heterogeneous nucleation occurring. If you just add any type of particle to a liquid, it does not give you heterogeneous nucleation. Simply take let us say aluminum, add some sand particles to it, it does not give you, though you may say, sir, there are particles available. That particle that you are adding should have a structural compatibility with the solid that is nucleating, such that the interfacial energy between the solid and this the particle that is available should be very small, so that this is minimized. And that is why if you remember, again I will take you back to your heterogeneous nucleation. Think of a particle here and a solid nucleating, and there is a liquid. So, you should know that if when the solidification has not taken place, if the solid has not formed, then what you have is only particle liquid interface, is not it? You have a particle, you have a liquid, solid has not formed on it. So, you have a gamma PL. The moment a solid has formed on it and this gamma PL has some surface area, so you have a into gamma PL will decide what is the total interfacial energy of that particular system. there is a particle inside a liquid. Now, the moment there is a solid that nucleates on the particle, now you have different interfaces. You have a particle solid interface, you have a solid liquid interface also, is not it. So, a particle liquid interface which was in this area has been now replaced with particle solid interface and solid liquid interface. So, you will have A gamma A into A of SL into gamma of SL plus A of PS into gamma of PS. These two are replacing A of PL into gamma of PL. If this is smaller than this, if this combination is smaller than this, then only the heterogeneous nucleation will take place, because you can see here this interface is replaced with two interfaces. There is a particle liquid interface and particle solid interface, which is actually a circular interface, because it is a plane surface on which you have a hill forming, okay, a bubble kind of solid forming, let us say. So, this interface is circular, whereas this is like a spherical cap. The solid liquid interface is a spherical cap. Whatever geometrically you can calculate what is the area of that. You calculate the area, multiply with the gamma of that particular thing. Similarly, calculate this PS area, which is this. So, actually APS is equal to APL. Before the solid has nucleated, these two surfaces are the same. It is something like a flat surface, and in that a circular area a solid has nucleated and solid has formed like a balloon. And so, this area before the solid has nucleated, it was actually a particle liquid interface. So, I can say that this is equal to this. So, considering these two total surface energies, this overall surface energy has to be smaller than that, then only you would have heterogeneous nucleation. So, whenever I say heterogeneous nucleation is taking place, when does that happen? It happens when this is very small. When gamma PS is very, because gamma SL does not depend on what particle I am adding. Gamma SL is between liquid and solid, that has nothing to do with which particle I have added, but it is gamma PS is decided by actually the structural compatibility between the solid and particle. Whenever you see the particle has the same structure, has a very similar structure, that is the reason why when I take an aluminum alloy, I add a TiB2 particle, it acts as a good nucleating site. Why? Because the TiB2 has a structure which is hexagonal, and whenever you have a hexagonal structure, there is some similarity between hexagonal structure and aluminum. What is the structure of aluminum? FCC. What is the similarity between these two? Yes, some plane of FCC has a similar packing to that of another plane in HCP. The basal plane of HCP and the 111 plane of FCC have exactly similarity. So, on the basal plane of a TiB2 particle, actually a aluminum can grow, and that is how the actual nucleation takes place. And just because structures are same, I mean there is a compatibility, that is not sufficient. What you have to also look is what is the interatomic distance in the basal plane and what is the interatomic distance in the 111 plane is also important, otherwise there is strain during this nucleation. Okay. So, that is why we actually, when we talk about different particles being added, we look at whether first of all there is a structural compatibility. For example, if I add a cubic particle into an aluminum, for example titanium carbide is a wonderful nucleating site for aluminum because it is cubic. If I add a cubic particle, because aluminum is cubic, it has a easy compatibility. But if I keep on adding different cubic particles, but with different lattice parameters, and at some stage you see that lattice parameter of this cubic particle that I am adding is entirely different from that of the aluminum lattice parameter, still it will, though it is cubic, it may not nucleate. So, all that is reflected in terms of one single parameter called gamma PS. So, that is why we talk in terms of what is called coherent interfaces, semi coherent interfaces, all that comes from here when there is a compatibility, lattice parameter compatibility, and you can see that when this is much smaller, so that this is satisfied, then only you have nucleation. Similarly here, when you have these three interfaces, the interface which has the lowest, in fact when I want to talk in terms of this, for example in case of eutectic, I have to split this A gamma into three parts. I have to say A of alpha beta into gamma of alpha beta plus A of alpha liquid into gamma of alpha liquid and A of beta liquid into gamma of beta liquid, because this is all three are together. So, I have to split this into three parts, and out of the three parts whichever is the lowest, the system would like to choose that, and that is the reason why wherever you see a lamellar eutectic, it means that actually alpha beta interfacial energy is the lowest. You can actually calculate it or see a handbook where the interfacial energies are available, and you would see that this is true. Whenever this is smallest, you will see that happening, and if one of these two is smaller, then what should happen? When one of these two is smaller, for example if I assume that alpha liquid interfacial energy is the smallest, then you see inside the liquid the alpha will nucleate first. The moment liquid alpha interfacial energy is smaller than alpha plus beta will never nucleate together as a couple. You will see alpha nucleating first, okay, and then the remaining liquid slowly converts to the beta, so that you will have a beta matrix and alpha particles. It can be alpha particles, it can be alpha needles, it can be alpha plates, depending on growth conditions. Certain structures of depending on what is the structure of alpha. For example, if you look at cementite is a particle in a laterite, whereas aluminum silicon eutectic, if I look at it, the silicon are needles. Why? Because the diamond cubic structure of silicon is such that some directions can grow much faster than the other directions. Maybe if you have read about solidification, the growth directions, okay, are different because in all directions the growth rates are not the same. Have you ever heard about it? For example, if I take a cubic structure, if I take aluminum nucleating inside we always say it is spherical nucleus. Actually first and foremost is never spherical, never a nucleus is spherical, excepting a situation where a liquid is nucleating out of a gas, because there is no crystal structure there. The moment you are talking of solid nucleating out of a liquid or a solid nucleating out of another solid, you can never ever have a spherical, because solid nucleus is composed of unit cells. It would tend to minimize the surface energy, not tend to become spherical. It would tend to minimize the surface energy by choosing such a shape which has the lowest surface energy, that which you think is sphere, but it is actually not that. Okay. Coming back to that point, okay, here you understand this, that it would be alpha that nucleates and grows, and then rest will be beta. And in the other case where liquid beta interfacial energy is lower, you will see beta nucleating and then growing. So, depending on what is the situation, you will have either different morphologies of alpha, but you will always see that there is no lamellar nature there. You will always see something growing inside the other one. So, when the eutectic reaction is finished, when you look at the microstructure, you will see one phase embedded in the other phase. The moment you see embedding of one phase in the other phase, you can easily understand, for example, silicon inside aluminum or cementite inside austenite, it clearly tells you that the cementite has nucleated first. Similarly, there also silicon has nucleated first than the alpha aluminum. So, by looking at the microstructure, we can know which has nucleated first, and that gives you an idea whose interfacial energy. Not only interfacial energy, I have to also caution you here, interfacial energy is one aspect. The second aspect that decides which will nucleate first is a structure. Okay. It is also the structure that decides, because if some structure of one of the two phases has a very complicated structure, let us say its nucleation is more difficult. So, the kinetics will force that one of the phase nucleates first rather than the other phase. So, that is also another point. Now, coming back to this point of shape of the nucleus, lot of people have worked on it, many. Have you heard of this gentleman by name this? Okay, of course, yeah, a whole thermodynamics that we talk about, the free energy that we talk about is Gibbs. Gibbs has worked on it for quite some time to understand what is the shape of the nucleus, and that is when he has realized that when I look at a particular a cube, let us say in a cube there are different phases, is not it, different planes in a cube. You have the 100 type, 110 type, 111 type, variety of phases. Each of them has a different surface energy. Do you accept this? The 100 plane will not have the same surface energy as 111 plane, is not it. In fact, that is the reason why when you take a polycrystalline metal and put an etchant on it and then see it in a microscope, you will see different shades. Some grains look black, some grains look bright, some grains look some grayish, is not it. You must have seen this. And what is the reason that we say? Yes, if you simply look at a sample with different grains, let us say, and let us this is grain 1, grain 2, grain 3, and if a light falls on it and goes back, and you are seeing the light which is coming through the eyepiece, and depending on what is when, and this happens only when I have an etchant there. I put an etchant, and what is this etchant doing? It is selectively dissolving different regions. Whichever regions are more reactive, it dissolves more, whichever regions are less reactive, it does not, and this reaction depends on the surface energy. The reason that is the reason why we start seeing the grain boundaries first. Why? Because grain boundaries are high energy regions, so they get attacked first. So, you see a pit formed there at the grain boundary. Once a pit is formed, the moment light enters there, okay, it does not get reflected back towards the objective, it goes out. So, the light that is coming through, it goes out like that. Once it goes out, it does not reach the objective, and if it does not reach the objective, you see it as black. That is why grain boundaries look black for you. Now, similarly, looking at these grains also dissolve in a different fashion. Why? Because if I look at the planes which are parallel to this surface, the planes that are parallel to this surface for grain 1, grain 2, grain 3 are not the same. The atomic planes I am talking about. So, for example, in grain 1 maybe the plane that is parallel to the surface may be 111 plane. In grain 2 it is impossible to have 111 plane parallel to the surface. Why? It is a different orientation. If it is if the same 111 plane is parallel to the surface, then I do not call it as grain 2, it would have both of them are the same grain. So, as a result you will see some other grain, some other plane maybe 100 is parallel, and maybe here 110 is parallel. Now, if you look at these, okay, each plane has a different surface energy, and what does that surface energy depend on? It depends on actually the number of broken bonds. If you think of a plane like this, there are atoms below it, but there are no atoms above it. Per unit area, how many number of atoms are not there decides the surface energy of it. The closest packed plane will always have, okay, a higher surface energy that way, because in a given area you have more number of atoms supposed to be there, above it there are no atoms, below it you have atoms. So, that is why you see different planes have different surface energies, and as a result you will see the etchant reacts. Now, what Gibbs has done is he tried to look at these surface energies and tried to form a shape of the what is called the nucleus based on these surface energies, and I think we will look at that possibly in the next class.